Dear students, today we will learn about interference of light. So I have written the definition. It is the phenomenon of redistribution of light energy due to superposition of light waves coming from two coherent sources. This definition needs a very comprehensive understanding. You must know what is coherent source, what is superposition, what is redistribution. So once you understand all of that, you will be able to give a meaning to this definition. Now suppose you have a single light source. It can be a point source or it can be a light source. It is giving light waves in all possible directions. So the pattern of distribution is uniform, right? Similarly, if you have a line source, it is also giving light waves in all possible directions, and the pattern of distribution is uniform. I may also give you an example that if I have 10 students in the class, 10 different students in the class, and I want to distribute 1000 rupees among them, I will be giving rupees 100 to each one of them. So it is 100, 100, 100 to each one of them. Again, the distribution is uniform. Right? Now if I ask the students who are standing at the odd position, say 1, 3, 5, 7 and 9, to hand over his or her 100 rupees to the next student, that is the even numbered student, then the new distribution will be 0, 200, 0, 200, 0, 200 and so on. So this is called as redistribution. Of course, the total sum, the total intensity is 1000. That is there, it didn't change, but the distribution has changed. So this is something that we call as redistribution. And this redistribution has happened on account of a phenomenon that is called interference. Now, you see that at certain places we obtained a zero intensity, a zero distribution, that is due to destructive interference. We call it destructive interference. And at certain places we obtained maximum intensity due to constructive interference. Now, in order to understand this constructive and destructive interference, let's go back to the coherent sources. What are two coherent sources? Two sources of light which have, remember, same wavelength, same amplitude, same frequency, and are moving in almost same direction. Those are called as coherent sources. The sources of light which have same wavelength, same amplitude, same frequency, moving almost in same direction are called as coherent sources. They have also same phase or a constant phase difference. I'm repeating, two light sources of same wavelength, same amplitude, nearly same frequency, moving in the same direction, having same phase or a constant phase difference are called as coherent sources. How are coherent sources obtained? They are obtained from a single source, remember. It's very difficult that two different sources of light can be coherent, so we choose to make them from the same source, single source, either by reflection or by refraction or by diffraction. Okay, suppose I have a light source here and I get a mirror image of this light source. So I have two sources of light now. Of course they are off because it is the mirror image of this light source. They have same wavelength, same frequency, same amplitude and so on. Or I can choose to obtain two virtual images of the same light source. They are also coherent. Now some more properties of coherent sources are they should be point sources, that is very narrow sources. They should be very close to each other. They should be preferably monochromatic. Preferably monochromatic. What do I mean by that? That they should be emitting single wavelength. So you have, for example, a light source of sodium only, of mercury only. So they will be emitting a particular wavelength, single wavelength. That's what we call monochromatic. So these light sources should be point sources, very narrow sources with least background. They should be close to each other and they should preferably be monochromatic. These are called as coherent sources. So once these coherent sources of light superimpose, they produce interference. And that interference gives us two patterns. One is constructive and another is destructive. All of you know that if we plot the graphics of a wave, it's like this. In case of constructive interference, the crest and crest of two waves, they superimpose. In case of destructive interference, a crest falls on a trough of another wave. So in this case, the crest and crest are overlapping. The resulting wave has a higher amplitude. In this case, the crest and trough are overlapping at a given time. The resulting wave is represented by this line that has the least amplitude or zero intensity. Right? So this is called as constructive interference, corresponding to which you will obtain bright spots in your experiment. Bright spots. And corresponding to destructive interference, you will obtain dark spots in your experiment. Now, the next thing is, how do we understand them in terms of phase and in terms of path difference? For example, again we plot the graphics of the wave. I hope all of you understand that we allot the phases in this way. It is 0, this is pi, this is 2 pi, this is 3 pi, this is 4 pi, and so on. If I choose another wave that begins from, say, this position, right? So its 0 is here, its pi is here, and so on, right? So what happens at this point of time? The crest of one is falling on the trough of another. We know that the resultant is going to be 0. But when did that happen? It happened when the phase difference was pi minus 0, that is pi, 2 pi minus pi, that is pi. Right? So when the phase difference was an odd multiple of pi, the resultant was that the crest of one falls over the trough of other. The resultant is a straight line, that is 0 intensity, that is a dark spot, and the phase difference is pi. Remember, odd multiple of pi. So we can choose to write that as 2n minus 1 times pi. Now if we choose this way, right, again this is 0, this is pi, this is 2 pi, this is 3 pi, and so on, and I choose another wave at this spot, right? So its 0 is here, its pi is here, its 2 pi is here, and so on. So what is the phase difference? The first thing is that at a given point of time, the crest of one falls over the crest of another, and the corresponding phase difference is 2 pi minus 0, that is 2 pi, right? So it is an even multiple of pi, right? So I can choose to write that it is n pi, 2n pi rather, to make it even, right? So when the phase difference is an even multiple of pi, the interference is constructive, and when it is an odd multiple of pi, the resultant is 0, that is, it gives us a dark spot. Now, corresponding to this, you also know that 2 pi corresponds to a full wavelength. When the phase difference is 2 pi, the total wavelength that has been closed is pi, right? So therefore, if you want to substitute for this pi, you will be writing lambda by 2. So for here, you can also choose to write 2n minus 1 lambda by 2. This is equivalently the same thing. And in this case, you can choose to write, for 2 pi, you will be writing lambda. So it is n lambda. So in terms of path length, path difference, the expression is n lambda, and in terms of phase difference, the expression is 2n pi in case of constructive interference, giving you bright spots, right? And in case of destructive interference, where the phase difference is an odd integral multiple of pi, the corresponding path difference is 2n minus 1 lambda by 2. How did we get that easily? I'm repeating that by substituting lambda for 2 pi. We know when a full phase difference is 2 pi, a full wavelength is lambda, right? Now the next thing that I want to tell you is about interference through division of wavefront and interference through division of wavefront and interference through division of amplitude. All of you are well aware about this wavefront. I have told you in detail about the wavefronts, how they are formed, how they propagate in the previous video. You are also aware about what is the amplitude of a wave. So if we obtain the phenomenon of interference by division of wavefront, we say it is interference by division of wavefront. And if we obtain the phenomenon of interference by division of amplitude or division of intensity, remember division of intensity, we say it is interference corresponding to division of amplitude. So let's try to understand those by means of examples. A popular example is that of Young's double slit experiment. We'll do that in the next lecture. Young's double slit experiment, right? What do? We have a line source or a point source. It is giving the semicircular wavefronts, and then we are dividing those wavefronts by two more slits at the other end, and we are obtaining the corresponding interference patterns, right? So this is an interference pattern that you have obtained by planning a scheme of experiment in which you are dividing the wavefront. So this is interference by division of wavefront. In this case, you need either a point source at the beginning or a line source. Both will work. In case of division of amplitude or division of intensity, what do? That you choose to reflect the light beam from two surfaces of a thin film, right? So one part gets reflected from this and another part gets reflected from this. This also introduces a path difference that is visible. You can understand that. Because the light is reflected from two different layers of a thin film, obviously we are dividing the intensity of light. Dividing the intensity. And since you know that intensity is actually proportional to the square of amplitude, we also say that this is the phenomenon of obtaining interference through division of amplitude. In that case, you will have to do Newton's rings apparatus. You will have to do Michelson's interferometer. Of course, you will be doing all these things in the lab work that I shall tell you in the subsequent videos. So I hope that gives you a fair idea of interference of light.